Hey folks, it's Mr. Woodward. Let's talk about power and the cost of electricity, the electricity that you have to buy from your electric company. So first of all, I want to start with a definition of power. Power is the rate at which energy is used by an electrical device. The rate at which energy is used. And if it's electrical power, it's the rate at which energy is used by an electrical device. Okay, so you've heard of power as, like a 60-watt light bulb. That's the measurement of the power of a light bulb. So taking a look here, if the goal of a circuit is to transform electric potential energy, which is in a battery, by the way, and I'll just make this note, electric potential energy, right, from a battery, or from some sort of a power supply, but often it's from a battery. If the goal of a circuit is to transform electric potential energy from a battery, for example, into other forms of energy, then we need a way of measuring how much energy is transformed each second. This is called power, and it is measured in watts. Okay? Power is the energy that's used in a unit of time. Right? That's why it's a rate. It's a rate at which energy is used. And the units of power are a watt, where 1 watt is 1 joule per second. Okay? A watt is a joule per second. We can derive an equation for power that is related to voltage and current. As a reminder, current is the flow of charge. Current is the amount of charge that's flowing past a point in a given amount of time. And voltage gives charges energy. So energy is the voltage times the charge. So our equation for power is that power is just current times voltage. Current times voltage. And in equation form, we write it like this. P equals I times V. Power is current times voltage. This, by the way, is called Joule's law, after James Joule. Joule's law. P equals I times V. So this is relating current and voltage to power. So let's try an example of this equation called Joule's law. So how much current flows through a 60-watt light bulb when it's plugged into a 120-volt outlet? That's the voltage that you get when you plug something into the wall, a wall outlet. So how much current? Well, let's start with Joule's law. Power is current times voltage. We know that the power is 60 watts. We don't know what the current is, but the voltage from the wall outlet is 120 volts. So we do the division, right? We would divide both sides by 120. Those cancel out. And so this means that the current is going to be 0.5. And then a watt divided by a volt is an amp. You may remember before that current is measured in the unit of amps. Okay, so how much do we pay for electricity, right? So it's one thing to be able to calculate power and relate it to current and voltage, but let's talk about money, right? How much does it actually cost? What's the cost here? In the Bay Area, we all pay PG&E, that's our local electric company, to supply our houses with voltage. Standard US outlets are 120 volts. That way we can plug in our appliances, which are really just a bunch of resistors, and then use them to transform electric potential energy into all types of energy: heat, sound, light, motion, etc. However, this costs money, and PG&E charges us not only to maintain this 120 volts at our house, but more significantly for the amount of energy that our home circuit consumes. In other words, we pay PG&E for the amount of electric potential energy that we use each month. That's why your parents want you to turn things off when you're not using them. It saves money. So how much does electric potential energy actually cost? And I'm up here. Normally we measure energy in joules, But 1 joule is very little energy. So here in America, we use a different unit called a kilowatt hour. Okay, you may have heard of a kilowatt hour before. That's the unit, by the way, that would show up on an electricity bill. So let's figure out how many joules 1 kilowatt hour actually is. Well, back from what we learned on the first page of this, by definition, 1 watt is 1 joule per second. Okay, so if we were to rearrange that, multiply both sides by seconds, we would get that a watt second is equal to a joule. Okay, well then let's go to this idea of a kilowatt hour, right? A kilowatt is 1,000 watt hours. Okay, so then we would multiply by 1,000, and we would get this, that a kilowatt hour is 1,000 watts, and an hour then into seconds is 3,600 seconds, and we would get 3.6 million watt seconds. Therefore, a kilowatt hour is equal to 3.6 million joules. That's the connection that I want to make here. Okay, a kilowatt hour is 3.6 million joules of energy. That's a lot. All right, so what does that actually look like, a kilowatt hour? So how much does 1 kilowatt hour cost? Well, the Bay Area is expensive compared to the rest of the country. In San Francisco, it costs about 22 cents for each kilowatt hour, compared to the national average of only around 13 cents. That may not seem like a lot, but it adds up when you think about how many appliances you have and how much wattage, right? Wattage means power. How much wattage or power they consume. So here in blue, we have San Francisco area. So we see all of the blue graphs are much higher. And then in red, we have the rest of the United States, okay? Much less. And so over the past years, and this is a little bit outdated, right? We're looking at from December of 2009 to December of 2013. Something around, and right, if you kind of draw the level of these blue line graphs in San Francisco, the average is around here, which is 0.22 or 22 cents per kilowatt hour for San Francisco, at least from 2009 to 2013. And that was from the Bureau of Labor Statistics. All right, so hold that number in your head, around 22 cents for each kilowatt hour of energy that you buy from PG&E. So what we're going to do next is we're going to actually run some calculations and figure out like how much does it cost to run an appliance for a day or a month or a year. And this is how you would do it. So to calculate how much it costs to run an appliance, you first calculate the energy, okay? And energy is power times time, because power is right, energy divided by time, the rate at which energy is used. So if you want to just calculate power, you would multiply both sides by time. But then cost is determined by the energy multiplied by the rate at which PG&E charges. So the cost is the energy times the rate. And so here's where we're going to land. Well, you already know that energy is power times time. So you're going to take this power times time and plug it in here. And so you get that cost is power. This is an algebraic substitution, right? Power times time times rate is cost. Cost is power times the time times the rate. That's a lot. That's a lot to multiply. And so essentially, it's just dimensional analysis. We're going from one dimension to the next. And so I'm not going to use like this specific formula that cost is equal to power times time times rate, as much as we will see that flesh itself out in a dimensional analysis problem. So we're going to do two of these. Starting here with a typical microwave. Okay, a typical microwave, I'm right here. A typical microwave has a power of about 800 watts. How much does it cost to use the microwave for 5 minutes in order to heat up a frozen dinner, right? You might have not thought of that before, but every time you heat up a frozen dinner, it actually costs money, not just for the dinner, but to even heat up the dinner. So we're going to start with the 800 watts. That's the power that the microwave is using. And then remember, one of the sort of hidden givens here, not in this problem, is that the rate is 22 cents per kilowatt hour, okay? I'm pulling that information from earlier, so we are going to use that as well. So we need to go from watts to kilowatts, and we'll use some dimensional analysis, okay? So we're going to go from watts to kilowatts, and by definition, 1 kilowatt is 1,000 watts. All right, so watts are gone. Now we're going to go from kilowatts to using this rate of 22 cents per kilowatt hour. So I'm going to have the kilowatt hour on the bottom, and I'm going to have the unit of dollars on the top. So we had 22 cents in 1 kilowatt hour. That's the rate. So now we're going to see that this kilowatt cancels out. So if we stopped here, the units would be dollars per hour. But we have 5 minutes. So now I need to convert from hours to minutes. So let's keep going. I'm going to try to get rid of these hours and eventually go to minutes, right? So we know that there are 60 minutes in 1 hour. So now I can cancel out the next thing. Hours will go away. And if we stopped here, my units would be dollars per minute, but I'm not going to stop there. I'm going to do one more step, which is to factor in the 5 minutes. And the 5 minutes is not a conversion factor. I'm using one of my givens here, okay? And what does that do? That cancels out the last thing, which is minutes go away, and now I will just be left with dollars. So if I multiply that all out, 800 divided by 1,000 times 0.22 divided by 60 times 5, I'm going to get $0.015. This is equivalent to 1.5 cents. So it costs you 1.5 cents in electricity to heat up that frozen dinner. That's pretty darn cheap, and amazing that we've been able to make electricity that inexpensive. Let's try the next one. How much does a 60-watt light bulb cost each month if it runs for a total of 5 days? Okay. Here we go. Let's start with the power, 60 watts. And then we're going to convert from watts to kilowatts because we want to use the rate of 22 cents per kilowatt hour. So there are 1,000 watts in 1 kilowatt. That makes the watts go away. Then I'm going to go the 22 cents per kilowatt hour. I'm going to write the 22 cents on top. Okay, 22 cents per kilowatt hour. That's going to cancel out the kilowatts. And then I can start to factor in the time, right? 5 days is where I'm headed. So I'm going to go from hours to days, right? There's 24 hours in 1 day, and I'm going to do that for, my bad, the last one is not a rate, 5 days. So what cancels out here? Hours cancel, and then days cancel. And so what's uncanceled? Dollars. 60 divided by 1,000 times 0.22 times 24 times 5 is 1.58, and that's dollars. So $1.58 to run a light bulb for 5 days. Also pretty darn cheap. So this is power and the cost of electricity.